Okay, to finish out this module on limits, we're going to talk about limits at infinity. And well, that's basically the kind of behavior that you have also seen before in algebra classes, most likely when you talked about rational functions. That's what's connected to horizontal asymptotes, oblique asymptotes, and the like. So let's see how we do that with limits. Why are those things important, first of all? Well, basically they allow us to say something about the long-term behavior of functions. And so if you've got any kind of a model that talks about a mechanical system or so, you'd like to know the steady state of that system. That's especially then also important in an electrical system where you might want to have a stable steady state kind of thing, and that's typically a limiting analysis. Graphically, we'll get asymptotes of functions when the asymptotes exist. And so, well, what are they? The definition, the informal definition of the limit of a function at infinity is the following. The number L is the limit of the function f as x approaches infinity, if and only if for all sufficiently large x, we have that f of x is close to L. So again, something that says outputs have to be close to a number when something happens with the input. Same pattern as what we had for the other kinds of limits. And in this case, we'll write that the limit as x goes to infinity, f of x is equal to L. Or f of x approaches L as x goes to infinity in this fashion also. And a function that has a limit as infinity is called convergent as x goes to infinity, and if it's not convergent, we will say that it is divergent. Okay, the corresponding definitions for limits at minus infinity, of course, are similar, and again, we've just built some vocabulary. Let's see what it does, right? Well, before we do that, make the connection to what you've seen before. Take a function, and if there's a real number h such that the limit as x goes to infinity of f of x is equal to h, then the horizontal line y equals h is called the horizontal asymptote of f as x approaches infinity. And we can define a horizontal asymptote for f as x approaches negative infinity similarly. And we'll see an example in this presentation that the two really can be different. Okay, visualization of this stuff is that you've got a function, and you want to look at the long-term behavior. And the long-term behavior, even though this thing is oscillating, is that it appears to be flattening out here around, that ought to be something like 2, I think, because it goes 1/2, 1, 1.5, 2. Didn't have that scale in there, but either way, it seems to be flattened out. It seems to stabilize at some kind of limit, and that's what limiting behavior really is. In particular, even though it very often happens for rational examples, especially for rational functions, there is nothing that forbids the function from crossing its own asymptote. That's a question that I get asked frequently in calculus classes, and no, a function can cross its asymptote. There is no problem with that. And in fact, we can see here this one, if this really is some kind of a damped sine wave that keeps oscillating around this horizontal asymptote, it'll cross the asymptote infinitely many times, and there's no problem with that. Okay, so how do we compute these things? Well, we, just like for the limit laws, we need elementary building blocks, and we need algebra. If c is a real number, well, then the limit as x goes to infinity of c is c. What's the limit of 5? It's 5, right? I mean, there's no problem there. The only other building block is that as x goes to infinity, 1 over x goes to 0. Because when x goes to infinity, you get 1 over larger and larger numbers. Well, 1 divided by a large number is close to 0, and in the limit, then we get 0 itself. Similarly, at minus infinity, c goes to c, and 1 over x still goes to 0. This time from below, but, well, 0 is 0. There is no plus 0 or minus 0. Okay, so the algebraic properties then are also very similar to what we've had before. If you've got two functions that are defined on some interval that starts at some point t and goes out to infinity, and if r is a real number, well, then if the two limits exist, then the limit of the sum is the sum of the limits. The limit of the difference is the difference of the limits. The limit of the product is the product of the limits. The limit of the quotient is the quotient of the limits, provided that the limit of the denominator is not 0. And the limit of a power is the power of the limit. This is exactly the same type of limit law setup as what we had for limits at a point. And we've got exactly the same problem as before, which is we need algebraic tricks to hopefully cancel 0 in the denominator, or things like infinity over infinity. And we will see those in just a second. The standard trick is that we would expand with the highest power from the denominator. So if we compute a very simple limit, like the limit as x goes to infinity of x over x plus 3, what we can see here is the numerator goes to infinity and the denominator goes to infinity, and well, infinity over infinity can't be computed. So what we do is we multiply with 1 over the highest power in the denominator, which in this case is 1 over x. So we're multiplying by 1 here. And that gives us a limit as x goes to infinity of x over x over x over x plus 3 over x. So that's the limit as x goes to infinity 1 over 1 plus 3 over x, and that's 1 over 1 plus 0, which is 1. Now notice that this is because the limit turns out that way. This is not because infinity over infinity gives us 1, and we'll see in the next example that indeed infinity over infinity can give us something other than 1 too. But again, just like for limits at a point, we can also double check. Here's the function x over x plus 3, and here's the horizontal asymptote, and we can see the function approaches its horizontal asymptote. And here's where you can also see for rational functions, they, well, very often they don't cross the asymptote, but like I said, there's nothing that forbids crossing the asymptote. Okay, compute the limits at plus and minus infinity of this function here. Now, in algebra class, you may have learned little theorems that say something about, well, the limit is the quotient of the leading coefficients, provided that the powers are the same, the highest powers are the same in numerator and denominator. And that kind of stuff often can devolve because, well, I mean, the quotient of the leading powers will be 4 over 5, and that's what the limit is going to be. But sometimes people just look at what's on the left, and then people might think that the limit is 3 or doesn't exist or something like that. And again, the idea here is solid algebra, even if it takes a little bit longer, solid algebra will get us the right result. And if it takes an extra line, it's just math, it's just algebra. I'd rather do an extra line and get it right than to try to quote some kind of theorem and accidentally apply it incorrectly and get the problem wrong. So what was the idea? You expand with the highest, with 1 over the highest power in the denominator. Highest power in the denominator is x to the 4th. So we expand with 1 over x to the 4th, multiply everything in. We'll get 3 over x squared plus 4 minus 7 over x to the 4th, and 1 over x to the 4th, 1 over x to the 3rd minus 3 over x to the 4th plus 5. There we go. 3 over x squared plus 4 minus 7 over x to the 4th over 1 over x cubed minus 3 over x to the 4th plus 5. And we keep the limit, of course. And now we can see, as x goes to infinity, number divided by stuff that's large, which happens here, 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 and here. That'll all go to 0. And so the limit is 0 plus 4 minus 0 over 0 minus 0 plus 5, and that's 4/5. And if we go to minus infinity, well, we do the same thing. We expand with 1 over x to the 4th. The limit as an expression looks exactly the same, only this time we go to minus infinity, and that limit is 4/5 too. And if we look at this graphically, the graph of this function, of course, is quite complicated, right? We're looking at a quotient of 2 4th order polynomials, so there's a couple of wiggles in there that you may not have seen in algebra class, because maybe examples have been a bit simpler. But what we're looking for here is the horizontal asymptote. 4/5 is 0.8, so that is around here. And the function as x goes to minus infinity and as x goes to plus infinity really approaches those asymptotes. Then we're looking at, yeah, sometimes the horizontal asymptotes turn out to be 0. That's what's going to happen here. The highest power in the denominator is x to the 5th. Okay, so we expand with 1 over x to the 5th. We end up with 3 over x to the 3rd plus 4 over x to the 5th divided by 2 over x to the 4th plus 1 over x to the 5th, like so. And of course that limit is 0 plus 0 over 0 plus 1 plus 0, so that ends up being 0. And of course as x goes to minus infinity, we do the same thing, and we end up with 0 as the limit too. And that's also reflected in the graph. Here's the graph of that function. And the asymptote, that's just a little color change here, because the asymptote is the horizontal line, y equals 0. Let me flip back and forth. You may be able to see that, or maybe not, but the asymptote is right here. And yes, the function does approach its asymptote as x goes to infinity and as x goes to minus infinity. Now, it can become almost a reflex to think that the limit at plus infinity and the limit at minus infinity are the same. And again, for rational functions, that typically is the case. But once you start looking at stuff that involves square roots, that will not be the case anymore. And here's how you handle this stuff. The limit as x goes to infinity of x cubed over root x to the 6 plus 1. Well, we still do the same thing. This time, however, we have to make sure we incorporate the root. And the way we do that is we read the denominator a little bit sloppy. The denominator is x to the 6 plus stuff, and then you take the square root. Square root of x to the 6 is x cubed. So you want to expand with 1 over x cubed. All right. Well, 1 over x cubed is the square root of 1 over x to the 6, because we need to get this underneath the square root. And now we can combine. Numerator will be 1. Denominator will be 1 square root of 1 plus 1 over x to the 6th, right? Well, I just combined it first like this, x cubed over square root x to the 6 over x to the 6 plus 1 over x to the 6th. Keep your limit sign around. And that's the limit as x goes to infinity of 1 over square root 1 plus 1 over x to the 6th, like I said. And that's 1 over square root 1 plus 0, which is 1. Great. So what could be different as we go to minus infinity? Well, we still have to expand with 1 over x cubed. But as we go to minus infinity, remember 1 over x cubed is negative, and yet this square root that we've had up here, square roots by definition are always positive. So 1 over x cubed as x goes to minus infinity actually is equal to negative square root of 1 over x to the 6th. And that extra negative sign now drags through the computation. We still get the x cubed over x cubed. We still get the square root x to the 6 over x to the 6 plus 1 over x to the 6, just like before. But this time we've got that extra negative sign out front here, which means we still get the limit as x goes to minus infinity here. There should be a negative sign here. Limit x goes to minus infinity, 1 over negative square root 1 plus 1 over x to the 6th. And that ends up being 1 over negative square root 1 plus 0. And that ends up being negative 1. Okay, remember, that should be a negative sign here. I apologize. So that means the computations give us different results. And if we don't want to believe those computations, it does look a little weird. Well, we can just look at the picture and we realize that the function really comes from negative 1, does a wiggle, and then goes up to 1. And so the horizontal asymptote for x going to plus infinity is 1, and the horizontal asymptote for x going to minus infinity is minus 1. Okay, good. That kind of thing we've also seen for the function arctangent of x, or tangent inverse of x. Remember, that's that snake-like thing, and it's got pi halves as the asymptote for x going to plus infinity, and it's got negative pi halves as the asymptote for x going to minus infinity. All right. Well, finally, what happens when your numerator has a higher power than the denominator? Let's take a look at that. Limit x going to infinity, x cubed minus 4x over x squared plus 1. We expand with 1 over x to the highest power in the denominator, so we expand with 1 over x squared. That gives us the limit of x, which is x cubed over x squared, minus 4 over x, which is 4x over x squared, divided by x squared over x squared, which is 1, plus 1 over x squared. And if we work that out, we get infinity, because x goes to infinity, 4 over x goes to 0, denominator goes to 1, infinity over 1, that's infinity. Similarly, as x goes to minus infinity, we expand with 1 over x squared. We end up with the same thing, and the limit is minus infinity this time around, because as x goes to minus infinity, this part here goes to minus infinity, and the rest, this goes to 0, this goes to 1, and this goes to 0. So we end up with this limit being minus infinity. And again, we can see in the picture that that's really what it is. Here's the graph. The function goes off to plus infinity. As x goes to plus infinity, it goes off to minus infinity. As x goes to minus infinity. And then we could say, well, now, it looks like it's getting close to a straight line. It's getting close to the straight line x. And that turns out to actually be the case. Because, and this is what is called the oblique asymptote. Let's first do the computation and then do the formalities this time around. In order to compute the oblique asymptotes, what you do is you actually do the division. You do a long division by polynomials. Let's see, x squared goes x times into x cubed. So x cubed divided by x squared is x. And x times x squared plus 1 gives us x cubed plus x. And that has to be subtracted. And that gives us a remainder. X cubed minus x cubed is gone. And negative 4x minus x is negative 5x. And negative 5x can't be divided by x squared anymore. So that quotient really is x. And that ends up being, therefore, the quotient is your oblique asymptote, so your quotient is that oblique asymptote y equals x right here. Now, the quotient will not always be a line that goes through the origin. Let's first define what these things are and then talk our way through a more complicated example. Two functions f and g are called asymptotically equal as x approaches infinity if and only if the limit of their difference goes to 0, or is 0. And if g happens to be a straight line, then we'll say that g is the oblique or slant asymptote of f as x approaches infinity. For example, we want to find the asymptotic behavior of 6x to the fourth minus 7x cubed plus 8x squared minus 10x plus 1 over 2x squared plus x minus 3. Well, that's not something where I can guess the asymptote, but I can always do the long division. So we set up the long division and we realize 6x to the fourth divided by 2x squared is 3x squared. 3x squared times 2x squared is 6x to the fourth. 3x squared times x is 3x cubed, and 3x squared times negative 3 is negative 9x squared. We have to subtract that, and we end up with 6x to the fourth minus 6x to the fourth is 0. Negative 7x cubed minus 3x cubed is negative 10x cubed. 8x squared minus negative 9x squared is 17x squared, and then we just copy down the rest. Sometimes you don't do that. It seems easier to me to copy everything down so you know what you still have to take into account. Negative 10x cubed divided by 2x squared is negative 5x, right? And so now we have to take negative 5x and multiply it by this. We get negative 5x times 2x squared is negative 10x cubed. Negative 5x times x is negative 5x squared. And negative 5x times negative 3 is 15x. And if we subtract that off, the 10x cubes go away. 17x squared minus 5x squared is 22x squared. Negative 10x minus 15x is negative 25x. And the plus 1 we copy down. And 22x squared divided by 2x squared is 11. Of course, that gives us 22x squared from here, 11x from here, and negative 33 from here. Do the subtraction, we end up with 0, and then 36x and plus 34, negative 33. And that means that our function is actually equal to the quotient 3x squared minus 5x plus 11 right here, plus the remainder, negative 36 plus 36x plus 34 divided by the denominator, which was 2x squared plus x minus 3, also seen here. And now we can see that, well, this part here, because the highest power in the denominator is x squared and the highest power in the numerator is x, this part here goes to 0, and that means f is asymptotically equal to this quadratic function 3x squared minus 5x plus 11. And we can also see that in the picture. The function, of course, looks quite complicated here, but the asymptotic behavior is this quadratic, and of course a quadratic is just a parabola, and that ends up just being that parabola that we've seen on the previous panel. Okay, finally, let's work at least one more problem with parameters, and again, remember, okay, parameters make things a little bit harder, but we ultimately will work with problems that involve a lot more than one variable. For example, you can remember the universal gas law. It's got 5 variables. If you correct that thing to the van der Waals equation, you get even more you get even more variables in there. And, well, we have no choice. This is a more accurate model, so sometimes we simply have to work with that. So we don't do ourselves a favor in working only with y equals f of x. We also need to work with stuff that involves parameters on the right side. Similarly, harmonic oscillators, the formula for the frequency contains 3 parameters, if you will, or one function, and that depends on 2 other things. The differential equation contains an awful lot of stuff that is given symbolically. And in terms of working with numbers, remember, I'd rather work with pi than to work with all these digits, right? So parameters will then make our solutions applicable to more problems. That's not going to be the case with the example we're working here. This is just a training example. But remember, when you describe quadratic functions, you just have parameters on the right side, and by knowing what the parameters mean, you can describe your function. And I think that shouldn't be k squared. That should just be k. Okay, let's just leave that alone for now. You can also optimize the surface area for rectangular boxes with given volume, with a fixed volume v, rather than for something where you just have a number. That way you can solve multiple problems at once. And again, solving more routine problems really is not the answer. In order to get used to working with parameters, in order to get accustomed with the stuff that we're working with in physics, the best thing to do is to just work with parameters, work with non-routine problems. So, and then yeah, routine problems are what computers are for. That's where you would just use a parameterization in order to program the problem. And finally, yeah, we can get some deeper symbolic insights by solving these harder problems. So let's do it. Find the number a so that the limit of this thing is equal to -2. Well, that looks pretty darn horrible. Well, so what are we looking for? We're looking for the limit as x goes to infinity, ax cubed minus 12 over a plus 1 x cubed divided by 3x squared minus 9. We expand with the highest, with 1 over the highest power in the denominator, so we expand with 1 over x cubed. Computation goes the same way. Ax cubed over x cubed is a, -12 over x cubed is -12 over x cubed. A plus 1 x cubed over x cubed is a plus 1. 3x squared over x cubed is 3 over x, and -9 times 1 over x cubed is -9 over x cubed. And now we can see as x goes to infinity, 12 over x cubed, 3 over x, and 9 over x cubed go to 0. So the limit is a over a plus 1, and we want that limit to be -2. Okay, so we just solve that. Well, if a over a plus 1 is -2, then a is -2a minus 2. 3a is -2, or a equals -2/3. And so that means the function would be -2/3 x cubed minus 12 from the numerator here. And -2/3 plus 1 is 1/3, so 1/3 x cubed plus 3x squared plus 9 in the denominator. And that limit really is -2. And with that, you've seen just about everything I think that we would want to present in a calculus class about limits. Remember, limits in many ways ultimately are what's under the hood. In calculus, limits are what allows us to define derivatives. Limits are what allows us to define integrals. But limits themselves may not be very much the object of your study, but nonetheless, we have built a conceptual foundation, and we have also built a symbolic foundation. We've done some algebra, and remember, anytime that happens, it's just algebra. We get it done, we move on, we focus on the concepts. No, we're not going to poo-poo the algebra because we've got to get it right, but other than that, it's just algebra. Once you can get it right, you can really say that. And we certainly have had enough practice in that here that now we should be ready to move on to derivatives. I'll see you there.